We'll finish this section with two applications of some of the formulas that we've seen, one of which is the length of a circular arc, right? And this is actually a fairly easy application. Earlier in this video series, we saw that theta was equal to S over R, where S is the arc length and R is the radius. And that told us the angular measure in radians. Well, what we could do is we could multiply both sides by R, and so r theta would be equal to s. That's where we derive this formula from. And our goal is to be able to find this arc length. Now, theta has to be in radians. Okay, so don't forget that when we have theta, it has to be in radians for us to be able to find that arc length. So let's compute each of the arc lengths, give the exact answer, and then round to 3 decimal places. So we have 2 pi thirds radians. All right, so it's already in radians. And then we have inches of 6 radius, or of radius of 6 inches, excuse me. So the arc length S is going to be equal to r theta, which in this case is going to be 6 times 2 pi over 3. Okay? And then if we wanted to, we know that 6 divided by 3 is 2. Okay? And so this would be equal to 4 pi radians or inch radians. Okay, so okay, or 4 pi inches, all right, since we don't want to put the radians in there. All right, so that'll be our unit, all right? Now, of course, that's our exact answer. And so the last thing we want to do is we want to approximate that. So we just go into our scientific calculator, and then we just take 4 pi, and that gives us 12.566. I think it said 3 decimal places, exact answer to 3 decimal places. So we said 12.566. All right, so that would be approximately 12.566 inches. All right, that probably means a little bit more to us than 4 pi inches. Right? Arc with a central angle of 135 and a radius of 3.75 centimeters. Now be careful. I see some students doing this often. So they take the 135 or they take 375 using our formula r theta, and they take that 3.75 and they multiply it by 135 degrees, but that is not correct. What we have to do first is we have to make sure that this angle is in radian measure. All right, so remember, to convert to radians, what we're going to do is we're going to take the angle, which is 135, we're going to multiply by pi over 180. All right, this should be 3 pi fourths, but let's just go ahead and verify that. So we take 135 divide 180 in our calculator, math, enter, enter, 3 pi fourths. All right, so that's the first thing we should do is if we're dealing with these arc lengths or if we're dealing with internal angles for radians, we have to make sure that we have our angle in radians. So now we can take this and multiply by 3 pi fourths, and then we can just multiply to get an exact value. All right, so we're going to take 3.75 times 3. All right, so in our calculator, we can take our 3.75 times 3, and we can divide that by 4. Right? And that gives us 45 over 16. Okay, now remember, you can hit math, enter, enter when you're done with this. All right, so the exact answer, okay, just like we said over here, is going to be 45 pi 16ths. But we want to try to get an approximate answer, right? So, and this would be in centimeters radian. But and so what we would do is we would just take this and put it in our calculators, and I would just take and multiply that by pi, and that gives us 8.836. All right, so this is going to be approximately 8.836 centimeters, okay, which probably means a lot more to us than 45 pi over 16, right? And again, that's just the length of this arc, okay? So that's what we're looking for, is we're just looking for that, that arc length. Now, one last thing that we're going to look at in this section is going to be angular and linear velocities, right? The linear speed is the rate at which the object moves along a circle, okay? So we call that v in this case, all right? And that's just going to go through and tell us how fast an object is moving in like this circular pattern. It's basically like a point on the circle, okay? So how many miles per hour, or how many feet per second it's moving. all right, and we just use that as v, okay? Um, and so what we do to figure that out is we could just take v equals s over t, where s equals r theta, where theta is in radians, okay? So another way to express v would be r theta divided by t, all right? So it's basically going to be the arc length over the time, all right? So that's not too bad. That's exactly what a rate is, okay? Now, the angular speed is basically the rate at which the interior angle is being swept out. Okay, so basically it's going to be this variable here. We call that omega. All right, so we have W as omega. That's just in Greek. All right, it kind of looks like this W. That's the best as I can draw it, and that's the rate at which the central angle is being swept out. Now, omega is equal to theta over time. Okay, that's actually even easier. So it's basically going to be the angle divided by the rate of time or the amount of time that it's moved. Now, what we could do is we could substitute back in for some of these variables. Okay, so notice that we have the velocity, the linear average speed is equal to s over t, all right, or theta, right? But remember, that theta over t is the same thing as omega. And so what we could do is if we know the angular speed and we know the radius, the measure of the radius, then we can express the linear speed as the radius times the angular speed. All right, so we're going to hold on to this formula because that's probably going to be the most important formula that we can get. Okay, these are all pretty easy to compute, but if we want to try to express the linear velocity or the linear speed in terms of the angular speed, then that's how we're going to do that. Okay. All right. So two really easy questions. Okay. So we have an angular speed on the point of a circle is 120 miles per hour. The radius is 30 feet. All right. Find the linear velocity in feet per hour of the point on the circle. All right. So the first thing we need to do is we need to be able to look at our formula. All right. And we have r theta. All right. But that means that we have to go through and we have to figure out what the angular velocity is going to be in radians. Okay, so first of all, let's just convert 120 times pi over 180, right? And if in our calculators, we should see this one's going to be 2 pi thirds. We've seen this one a lot, but of course we can always go back into our calculators. We do 120 divide 180, and that's going to give us 2/3 or 2 pi thirds. Okay, so that's going to be 2 pi thirds. And the unit for this is going to be radians per hour. Okay, so that's the time, it's per hour. And so if we go back up here to our formula, we know that the radius is 30 feet. We know that the angle is going to be 2 pi thirds. And then we know that the time t is going to be 1 hour. And so for our omega, or for, I'm sorry, our linear velocity v, because that's what we're ultimately trying to find. So remember, we said that v is going to be equal to our r times theta over t. And we know that the radius is 30 feet. And then we know that this is going to be 2 pi over 3 for every 1 hour. Right? And so that's going to give us our answer in feet per hour. So all we have to do really is just multiply 30 times 2 pi thirds. Right? And we could just go into our calculator, or off to the side, if we do 30 times 2 pi over 3, even easier, that's going to simplify to 10. And so that's going to be equal to 20 pi feet per hour. Right? And of course, if we want to try to approximate that, right, we could just type 20 pi into our calculator, and 20 pi is going to be 62.832 if we were rounded up to 3 decimal places. So 62.832 feet per hour. Right? So that's not so bad. Right? Again, all we're doing is we're just using our formulas and a little bit of rates so that way we can go through and get this down pretty nicely. All right. This one's a little bit sneakier, but not too bad. We have a bull wheel that drives a ski lift, has a diameter of 12 feet. The bull wheel is rotating at 18 revolutions per minute. We want to find the linear speed. All right, so one thing that we should do is we should try to figure out the angular velocity. And we know that it revolves 18 revolutions per minute. All right, so omega is going to be equal to, now we know that there's 2 pi radians for every 1 revolution. So that's just the angle. I mean, if we think about it, if we go 1 revolution, that's 2 pi. Now there's 18 revolutions. So there's going to be 18 revolutions for every 1 minute. And so the angular velocity for this, we're going to cancel out the revolutions, and that's going to be 36 pi radians for every 1 minute. Okay, so that's going to be our omega W. And if we go back up here, we could say that the linear velocity v is equal to the radius times omega. All right, and we know that the radius is not 12 because it has a diameter of 12 feet. So we know that the radius is d over 2. So that's going to be 12 feet divided by 2, which is 6 feet. All right, so now to find the linear velocity v, which is r omega, that's going to be equal to 6 feet times 36 pi radians for every 1 minute. Okay, now we don't need the radians because that's implicit. Okay, but that will give us our answer in feet per minute. If we multiply 6 times 36, that should give us 216. We have the pi, and then we have feet per minute. All right, now I'm going to go into the calculator just to make sure that I know what 6 times 36 is. 6 times 36 is indeed 216. We should probably get an approximation for this as well. So 216, we're going to multiply that by pi, and that's going to give us 678.584. That's going to be approximately 678.584 feet per minute. All right. And so that's how we can go through and use this angular velocity to help us find the linear velocity. All right. And most of the time in real life, linear velocity is going to be a little more important to us because that tells us how quickly something is moving in a circular motion. Okay. We can think of lots of things that move in a circular motion. Like we said, the bull wheel that drives a lift, car wheels, carousels, all kinds of things have these models of circular motion. Okay. So that's everything for our introduction to trigonometry. Right? So in the next section, what we're going to start doing is we're going to start defining trigonometric functions and also called circular functions. So we'll see what those are in our next series of videos.